Well, it's Sunday, and it's May, and it's the 19th of May. Sunday morning coming down. Old song. What Chris Christopherson. Listen to it sometimes. Well written. Uh, so I started the recording earlier. Uh, Getting a little jammed up here. Things are coming pretty fast. Have some extracurricular activities going on, and horses getting AI'd and some other things. But so this is going to be your week 7 preview. Uh, and I made a little list for myself and thought I'd share it with you. And there's some more than this, but we're going to visit what we've talked about before, types of soils in section 2 of your textbook. Uh, I have it up there. We won't spend much time on it because I think you've seen it a couple of times, but when you break it down, you have cohesionless, that's a coarse grained soil. You have like sand and gravel. Uh, you have cohesive soils, those are fine grains such as silt and clay. And then you have your organic soils, which goes in the garden. And it's your topsoil. It's when you start a project, you want to get rid of all the organics because you can't build anything on it because it's in the process of uh, deterior- uh, deteriorating constantly. So it's only going to get worse. So when we start a project, we go into the site and we take up all of the about 6 inches of dirt, which is topsoil, and we save it for when we get through building whatever they're going to put on there, and it gets spread back over the bare uh, inorganic material. That's what the foundation is sitting on, and the subgrade is, so they can have vegetation and keep the sedimentation down, and you have a lawn and all that kind of stuff. And we're going to talk about particle size distribution. You don't have the same size particle, and it's better that you have particles of different sizes in different places. We will talk about a little bit about gravel and the classification of soils. Gravel is anything that's greater than 2 millimeters. It won't pass that sieve. I forget which one it is, but it's less than 75. I mean, it's greater than 2, so it won't pass the number. Uh, what is that? The number? Well, I can't remember. Just give me a minute. The number 10 sieve. It won't pass it. Because let's see, 75 millimeters is well, I've lost my dang place. It won't. It'll uh, gravel will not pass the number 200, but coarse sand will pass the. It'll write the sand down there is greater than the number the 2.0 millimeter sieve, and it's greater than the 425 sieve. Now, we can start off with talking about why we're going to do these things. So, but the first thing I want you to see is it's kind of this practice thing. Number work in process project. This is an AASHTO. This is an AASHTO uh, classification system chart, and it has general classifications over here. We'll get more involved in this. I know it's a little hard to read, but the rest of the stuff I got's a little bigger. 35% or less of total soil sample passing the number 200 sieve classifies it as a granular material. If you have more than 35% passing the number 200 sieve, you have a fine grained soil. So you don't have to even mess with this section right here because it's not going to apply. You will be dealing with A4 through A7 if you have more than 35% of the soil passing I'm moving this around and it's freaking out on the number 200 sieve. It's granular soil. So that's the first thing. That means we can rule out coarse grain if we have that. More, 35% or less than or equal to 35% passing the 75,000 sieve or number 200 sieve is a granular soil. Now, we're going to look at a grain size analysis. We're going to calculate the sieve analysis. It looks like an X, but it's not. The sieve analysis data to plot a grain size distribution curve. We're going to determine grain size for calculating the coefficient of curvature, which is this formula, and the coefficient of uniformity, which is this formula. These coefficients tell you about something, and we'll get to that later. And they're also handy for getting into the unified soil classification system, which I doubt we will make it there. Maybe we will, maybe we won't, but we want to get this AASHTO thing down. So these are the things we'll be going over. Now, having said that, or I don't know why I said having said that, I want to go back and I want to look at the book and a problem that's in the book. And I think I can do that by clicking around a little bit here, a little bit there, a little bit here, and there we are in the book. So what you're looking at now is your textbook. I hope you have been reading your textbook. There's a lot of good information in there. But what we opened this up on happens to be a problem. And it's called Example 2, and it's on page 8, I think, in your textbook. And I have already worked through it, but we're going to go through what I've worked on. As you can see, the problem states that you're given a dry soil sample weighing 2,000 grams and it's brought to the soil laboratory for mechanical grain size analysis. The data are as followed. This is an abbreviated data thing here, just to get you going, but it has all the sieve sizes and the opening size of each sieve in millimeters and the mass retained in each sieve. Everything in sieve, everything 3/4 inch and below went through all the sieves. There was nothing retained. There was 158 grams retained when going through the 3/8 inch sieve. 158 grams did not make it through the 3/8 sieve. So you weigh that sieve and you got 158 grams. Same thing here. You weighed that because that's how much didn't pass the number 4. This is how many grams didn't pass the number 10, and so on. And this is an important game changer right here, the number 2 sieves. Remember I told you a while ago, 35% or less. If 35, let me make sure I'm saying that right. if you have 35% or less of the total sample passing the number 200 sieve, then you have a granular soil. So I can look at this thing real quick and say we're probably going to have a granular soil because that's not very much retained in there. Most of it has been sieved out. So that means to me that we probably have mostly fines. But we'll see. That's what the analysis is about. Now, I'm shuffling around different papers talking about a couple of different things, but they're all related. So this is the problem that we need to work out. And why can't I move it? Because I'm on the wrong thing. Okay. This is the problem we need to work out. Where does the daggum problem? Oh, we're gonna, let's go back a page so I can read what that sentence says and you can too. So here's your sieve analysis, and down here is saying at the end of the procedure, that's pouring all the sand in this top deal, you put it in a shaker like they have at Home Depot to stir the paint up, and you're shaking it, and all this sand that will goes all the way down to the pan, which catches everything that made it through all the sieves. Each of these sieves have different size screens at the bottom, like the number uh, uh, 200 has like 0.0475 openings in it. That's be so a bunch of like it's smaller than a screen door, I would think. That would be. But anyway, getting back to the analysis, the properties of a soil are greatly influenced by the size of the particles and, like I said, the distribution of their sizes throughout the soil mass. You know, like how is it distributed? Do we have the same particles covering up more area than different size particles scattered out? Well, we need different size particles to have a good soil. Table 2-2. So the certain sieve size open between 4.75 and 0.075 millimeters are designated by the U.S. standard sieve numbers as given in table 2-2. Here's the U.S. sieve. These will be all dealt with when we're calculating, classifying soil in the AASHTO. And right now, we need to arrive at how much soil passed each of these sieves. In other words, what was the percent of the sample that passed the number 4? What was the percent of the sample that passed the number 10, and so on? We got to calculate all that, and I'm going to show you how we're going to do it. At the end of the procedure, the soil particles retained on each sieve can be weighed and the result presented graphically in the form of a grain size distribution curve. Grain size distribution curve. See, I got all these dang pieces of paper out here. Just a quick glance. No, not a quick glance. A grain size distribution curve, which you will see in a moment. This is telling you this problem. Let's read it. An air dry soil sample weighing 2,000 grams is brought to the soils lab for mechanical grain size analysis. The data are as followed, and here it is. This is the mass retained in each of the sieves here. So it says what we need to do, a grain size distribution curve is what we're going to develop for this soil sample. The solution to required a grain size distribution curve. To plot the grain size distribution curve, you must first calculate the percent retained, and we'll get to that. On each sieve, the cumulative percentage retained and the percentage passing through each sieve. Then tabulate the results as shown in table 2.3. And that is this table. So we take the, this is the sieves we're going through. The number 3/4, well, the 3/4 inch, the 3/8, and the number 4, all the way through the number 10, and then we'll have the pan will have 100% retained in it. The rest will be passed almost, except for this little character right here. This is what tells me we probably have a coarse grain soil already. Tells me. So how do we get from here? How do we know the sieve openings? This is given the grams retained per for each sieve. And this is what we got to calculate. We got to calculate the percentage retained, and we need to calculate the cumulative percentage retained. So when we get this percent retained, to get the cumulative percent retained, we have to take this percent that was calculated dividing 158 by 2,000. You can do that in your head, I'm sure. And you'll come up and multiply that times 100, and you'll come up with 7.9%. Now, to get the cumulative percentage, you take the last percent retained, which is 0, and add it to this to get the cumulative. So 0 plus 7.9 is 7.9. So the cumulative percent retained here in sieve number, or the 3/8 inch sieve, is 7.9%. Now, we move down. In the sieve number, where are we? Sieve number 4, there's 15.4% of that weight, 15.4. Let me get back just a little bit. The mass retained here is 158 grams. So you divide that by 2,000, you get 7.9. You add that to 0, you get 7.9. You go back to the number 4 sieve, you have 308 grams retained. You take that, multiply it times 100, you get 15.4%. You add 15.479, you get 23.3. Now, I could have done this while you were watching, and I still can. That if I have the form, I don't think that's really necessary, but I do think it's necessary that you kind of look at the way I did it. You've got to go back to what's known as Elmo. And here is that view. Let's hope it gets a little clearer. To make this legible, times 100. Okay, so you can see some similarities here. I don't know why we're not focusing. Let's see if I can move this out of the way, and we can still see it. I don't want to fool around with this a whole lot. I think that's probably as good as we're going to get. There we go. That's probably good enough. So let's go through my calculations here. And if I was you, I'd go through with you. I sent you one of these sheets. I don't think I sent you with the information given, but you can get this information from the book. All of this comes from the book as I was looking that we were looking at. So now we're calculating. The book lays it out in long form for calculating the cumulative percentage retained. We don't want to stop with this. We need cumulative percent retained. So for now, pay no attention to these 100s, okay? And know that all of these are going to be multiplied times 100 to get this percentage, to change this, to get the percent of what 652 grams, you can't see me, to get this percentage of the total 2,000 grams, you divide this by 2,000 and you multiply it times 100, you'll get 32.6%. So that's what I'm doing every time. And I'll keep moving this paper around. So we start with the 3/8 inch sieve. And so this opening is 9.5 millimeters, and it retained, mass retained, it retained 158 grams. We'll divide that by 200, multiply that answer times 100, and you get, that was probably 0.079, multiply it by 100 and you get 7.9%. So just put that, it doesn't really have to go here, it can go straight here because this is just percent retained. So now to get the cumulative percent, I add the previous calculation of the 3/4 inch, and as you can see, it didn't get anywhere. It went through everything, it looks like. So 100% passed in it. It just all went through. So, but we have to put a 0 in here, and then to get cumulative, right here, 79, I take 0 plus 7.9 equals 7.9. Again, don't pay attention to this yet. We're not there. Move down to the number 4 sieve, which has a retained amount of 308 grams. Divide that by 2,000 and multiply that answer times 100, and you'll get 15.4%. And again, you can just put it in over here. I don't know why I kept putting it in there. You can put it right over here. Now to get your cumulative percent, you take the previous percent retained and add it to the current percent. You take the percent retained of the 3/8 inch, that's right here, and you add it to the percent retained of the number 4. So you're adding the previous with the current retained. So that gives you, I don't want this over here. Why am I over there? What's going on here? Let me stay in my lane here. Once again, 7.9% right here, because you took 0. You took 158 grams divided by 200. You got 7.9%. To get your cumulative percent, you added 0, the previous retained, which was 0, to 7.9, and that left you with the same 7.9. Moving on to number 4, you have 308 grams divided by 2,000 and multiplied 100 gives you 15.4% retained. And again, go ahead and put it over here. And don't worry about the 100 right now. Take this 7.9 plus 15.4 and you get 23.3% retained. Go down to sieve number 10. You will get, it retains 608 grams. And again, divide that by 2,000 and you get, let me divide it. It won't take me long because I feel like that you won't get as lost. It'll slow me down a little bit. So, where does that need to be? So I'm going to do it here. I'm going to take, which one am I on? Let's do 308. Mass retained 308 out of the number 4 sieve. My calculator here. So I'm going to take 308. I'm going to divide it by 2000. I'm going to get the equal of that, the equivalent of that. That's 0.154. I'm going to multiply that times 100, and that's going to give me the percent retained in sieve number 4 is 15.4. Now I'm going to take this 7.9% from the previous sieve, which is 3/8, and I'm going to add it to the current sieve of 15.4% at number 4 sieve retained, and that's going to give me 23.3%. So the way I do that is I take the 308, I divide it by, I don't even think you can see the calculator. I divide it by 2000, and that gives me 0.154, and I'm going to multiply that times 100, and that's going to give me 15.4%. So that's when I add, and I'm going to take that 15.4, and I'm going to, so this is kind of helpful, just take that 15.4 in my calculator, add 7.9, that speeds it up, and that's going to equal 23.3%. So now we can go down to the next sieve, which is number 10, and it has 608 grams retained. So I want the percentage, the mass retained is 608. I need to convert it to a percentage. So I take the mass retained is 608. So I need to convert that to a percentage. So I take 608 divided by 2000, and that equals 0.304 times 100, and that will give me, I messed up. Let me start over. I take the 608 from the number 10 sieve, retained in the number 10 sieve. I'll divide that by 100, by 2000, 08 divided by 2000, and that equals 0.304. Multiply that times 100, and that gives me 30.4% retained in that number 10 sieve. And if I take that right there and I add the 23.3 plus 23 point, if I take the 30.4% and I add it to the 23.3, I will get 53.7, the cumulated percentage retained in sieve number 10. When we get to sieve number 40, I have 652% retained. So that's 652 divided by 2000. Are you getting tired of me doing this? That equals 0.326. So I multiply that times 100, and that gives me 32.6%. And I take that 32.6 and add it to that 53.8, and that gives me 86.3%. I think that's wrong. Take the 652 divided by 2000, equals 3.326 times 100 equals 32.6 plus 53.7, 86.3, 86.3, 86.3. Okay, that's good. Now we keep doing that, and then we get down to the pan. And in this case, the pan had 8 grams in it, and I divided that by 2,000. Are we showing that? No, we're not to the pan. We're not to the pan. We're at the, we get down to the, I do the same thing with the number 40, and I add that, and I get 86. With the number 100, it had 224, so my percentage dropped to 11.2. Most of these have been a little higher because there's been more mass in them. But you take 224 divided by that, multiply 100, you'll get 11.2%. Add 86.3 to that, and you get 97.5%. The same thing when we get down here. Now here's the critical one. Here's the one we keep looking for. This guy right here, this number 200. As you see, its size is 75 thousandths millimeter. 75 thousandth millimeter of a millimeter. So we take the 42 grams and we divide it by 2,000. It gives us 2.1%. And we take that and add it to 97.5%, and that gives us 99.6%. So you can see real quick that we're got a gravel or coarse sand. So, but we do the pan just to make it happen. 1,000 divided by 2,000 times 100. Let me do that. Where'd it go? 0.4 divided by 2,000 equals way 0.0002 times 100 gives me that's not right. Let me do that over. There's a mistake here. Right quick. I'm gonna go back one. I'm gonna take I probably read a wrong number. Maybe that one. I'm gonna take this 200 sieve again, and I'm going to divide it by 100. There's 42 grams in there. 42 divided by 100 equals 0.52. There is that my mistake? I'm getting something. What's going on here? Let me slow down a minute. Let me go back to this one right here and take the 224 divided by 2,000 equals 0.112 times 100 equals 11.2 times 100 equals, sorry, I've already got the percent right here, so I take 11.2 plus 86.3, and that equals, I've got a distraction going on here, sorry. So at the number 100 sieve, we have percent retained, 11.2% retained. So I have to add that plus the 86.3% from the previous one plus 86.3, and that gives me 97.5%. That plus that's 97.5. And then I got to take this, I'm going to check my math on the number 200 sieve. That was 42 divided by 2,000 equals 0.02 times 100 equals 2.1%. So we're good there. And I got to add that to the previous 97.5 plus 97.5. That equals 96.6%. Now, I take the pan, I got right here's my last, next to last, 96.6. But we can see right away that I'm going to come up with 100, right? 96.6 plus 0.4% equals 100% passing the cumulative, and that's what it should be. It should come up as 100% to be cumulative. Now, what does that tell us? Nothing yet. Let's go up here. Now we go to these 100. The way to come to arrive at the percent passing is subtract the cumulative percent of each sieve from 100%. So let's start here. 100 minus 7.9 is 92.1. 15.4, I'm sorry, 23.3%. 100 minus 23.3 is 76.7. 100 minus 53.7 is 46.3. 100 times 86.3 is 13.7% passing the number 40. And 197% compute from the 100 sieve, cumulative. 100 minus that is 2.5% passing the 100. And when we get down here to the 200, we have 99.6 cumulative percent. To get the passing, we take 100 minus 99, and it gives us 0.4% passing. So that is less than 35%. So we can rule that we have a granular. We can rule out A4 through A7. We're dealing with A1 through A only through probably A2. All those, and there's little subgroups like A26, A27, and those are calculated with liquid limit and things like that. But that takes care of our percent passing. I don't, this is for sure not going to add up to 100%. It's not supposed to because it's cumulative. And where did that come from? Oh, 100 minus 7.9 is 92.1%. This threw me off up here. So this is what that problem requires you to do. Now you have the percent passing. And what I've done is I've grabbed this pre-worked on sheet, worked out and checked, hopefully. And if you notice, I have rewritten percent passings down here. I think I have. Yeah. The 3/4 inch, as you can see, is 100% passing. The 3/8% is, where's that? Is 92.1%. I don't think you can see these. 92.1%. Let's see if we can get this over in the limelight a little bit. it's never going to line up. But if you look at the number 4 sieve over here is number 4 is 76.7 as it is here. The number 10 sieve is 46.3, and the number 10 sieve over here is that's different, 46.3. So you can see I've got all of these. The number 40 is 13.7 over here. The number 40 is 13.7 over here. The number 100 is 11.2. No, wait. It's 0.15% passing, and that makes it, what have I got down there? That's a 2. That's really been corrected. This is 2.5. Where's all my pencils? This number right here, and I can see it is now, is a 2. 2.5%, as it is over here for the 100 is 2.5%, as you can see. And the number 10 is, that's what we just talked about. The number 200 is 0.4%, as we just came up with a little bit ago. So I've got them all over here. Now, what I've got to do now, once these are over here, is calculate the coefficient of uniformity and the coefficient of curvature, and they're abbreviated just like this. So, and here's the formula for uniformity: is the diameter particle size, that whatever particle size passes the it occupies 60% of the chart goes here. So for some reason I put 3 there. Let's look and go up here to 60%. I got to make sure you can see me, and go draw a line, hit the curve, and go down, and you'll see that they're 3 millimeters. So 3.0 equals 3 millimeters. I got stuff written all over here, as you can't see here. 3.0, I'm sorry, the D60 is 3.0 because I took the 60 and I went all the way across. I wonder if I could do this. I need to make room to ramble. Are we getting any better? I think so. Got a light up here that's supposed to shine on it. That will shine on it if I get it just right. Okay, let's see if we can rumble through this thing. Oh, get my pencil out, and as I was saying, I still feel like we're a little messed up. It's a little hard to read, but let's see what we can do. We can see a 3 here. So here's the 60, and we're going to go across, and till we hit the curve, and then we come straight down, and that particle size for the D60 is going to be 3. So let's go over here And look where I wrote them. D60 particle size is 3 millimeters. Okay, so let's go look at the D30 right here. So we go up here and we find 30%. And we come across till we hit the curve that we plotted. I plotted earlier, the book plotted. And we come down and we're at particle size 1 because here is 0.1 and there are 10 lines to here, so this is 1.0. That is the D30. So let's go over here and look at D30. I got it as, no, that's D60. D30 is 1. So let's look at the D10. Go over here to the 10. This is all passing. Am I saying that right? This is percent passing, all of this. So what was the diameter of the percent of the particle at 10% passing? It was, you go all the way to the curve, you drop down and you'll see it's 0.3. Now, did I get that right here? Yes, 0.3 right here. So we have enough information to calculate this coefficient of uniformity and curvature. Excuse me. I haven't figured out how to pause this. I'm using, I think it's CBO video. If anybody's familiar with that, I think that would be it, CBO. Let's see, make sure. OBS. I don't know why I got that. I'm using OBS video app. If anybody's familiar with that, tell me, figure out how to pause it so I can cough and move around a little bit. Okay, so we're going to figure out, let's calculate the curvature of uniformity. Well, we got to take D60, this is the formula, take D60 divided by 10, and that's going to give us, what is that going to give? D60 divided by 10 will be 3 divided by 3, and that's going to give us, what is 3 divided by 3? Come here, calculator. 3 divided by 0.3. Is 10. So that the coefficient of uniformity is 10. So I got WG here. That tells me I think it's well graded. Well, look down here. Coefficient of uniformity is much higher, even like 50. Instead of 10, this is 15, it'd even be better well graded. So it's saying, though, that the curvature of uniformity, when it's much greater than 1, the grain size spans a lot of area. And what that means is, looking at this, there's particles, different sized particles, all the way from sieve 3/4 inch all the way to 100. So this is a very well distributed. So when you see something like this, just picking up a chart, you know you got a well-graded soil. And we're just proving it right now. So let's go ahead and calculate the coefficient of curvature. Well, those D is 30 and D60, I'm sorry, D30 is 1 squared because D30 needs to be squared. So I've got 1 squared equals 1. D60 times D10. So D60 is 3 times 0.3 for D10. And I have that as 0.9. Let's double check that. In other words, well, 3 would be 0.9, wouldn't it? You can tell by looking at that. I'll do it anyway. 0.3 times 3 equals 0.9. That's what I have. So this is a little hard to understand. When the coefficient of curvature is less than, well, I got it down here 1, or it's greater than 3, the curve is not smooth. It means it's well graded. Uh, if this curve just kind of went up and around and up, just all over the place, if it's not smooth, it's not well graded. So I'm thinking up here, I'm saying the coefficient of curvature is less than 1 and greater than 3. I'm saying it's a smooth curve again, and then this soil, but this is saying if it's less than 1 or greater than 3, it's poorly graded. I think I have a mistake here, and we will find that out. I don't want to take up any more of your time, but the rules are in your book about these coefficients of curvature, what makes them indicates a good soil and what indicates a not so good soil. As a matter of fact, I think I got these from somewhere else, but let's get back to the book. We only so we can cut this thing short. Oh, by the way, in week 7 there is a read these before going any further. Uh, uh, let's see. We'll find the about the coefficient of curvature uh, because it's a little bit confusing. Uh, right here, this right here I know is right. It's poorly graded. When the grains are all the same, uh, it's poorly graded. This right here uh, says the grain side spans a lot of error, so this is well graded. This is poorly graded. I think one of these is wrong. I'm not sure. Uh, but I will double check that so we can get it. But what I'm interested in you being able to do is understand what we're doing. These are in your book. I really don't want to go into that right now, but I do want to show you some things here, which would be having to go back to my other screen if I can. Right here. And this week 7 discussion has some good, a couple of good videos in it. There'll be a video of this teaching assistant, I guess he's upperclassman, post-secondary, postgraduate student, talking about the AASHTO, uh, what the things we've been talking about. And then this Lorraine gal that's pretty good. She does a percent passing calculation and then goes on into taking her results and putting them in an AASHTO uh, chart so that she can come up with a soil type. And we're going to get to that. It's just that we're chapter 8 will just be a continuation of chapter. Week 8 will be a continuation of this. There is an assignment, and I think what I've asked you to do is just calculate this right here, the liquid limit and this plastic limit. In this case, you're not doing an AASHTO chart, so this won't be a necessity, but these are all what would go in a chart when you came up with the percent passing. Another way to say that is percent finder. So you got to get the percentage of total. So the number 4 would be 45 divided by 375, as you see up here. That's the total. And then multiply that times 100, and that will give you your percent passing and percent your you'll get your percent of total right here. I'm sorry, and by taking 45 times divided by 375 times 100, put that percent in here, and then add the previous. You don't have a previous one here. So your cumulative would be the same thing. Just put it whatever percent. Once you divide this by 200, you get a percent. Just put it here and then add the one above, which is nothing. So just move that one over here. And then you take the 3.6 grams divided by 2,000, put that number in and add it to that one, and that would give you cumulative right here. Make sense? Take that one, it's kind of like we just did, and divide it by the total, 375, multiply that. Let's see what that is in real world. In this case, you would take, what are we on, 3 points? We're on, yeah, 3.6. 3.6 divided by the total mass of 375 equals, that equals 0.0096 times 100, and that equals times 0.96%. Do that again. I'm going to do the next one to make sure I'm doing it right. If it don't look right, I don't like it. I'll move on. Let's do this first one. 4.5 divided by 375 equals 0.12 times 100 equals, so you got 12% right here, but you have nothing above, so 12% would go right there. In this one, it's 3.6. 3.6 divided by 375 equals 0.0096 times 100 equals 0.96% goes in that thing. Add it to, I forgot what that was, and then you would put your this plus this equals this. That would be your cumulative. And remember, when you get all of these cumulatives done, you subtract each cumulative from 100, right? 100 minus, 100 minus, 100 minus. You got it? Go back to my video and pause it and watch it. Take a look at it and you'll see what I've done. You shouldn't have any trouble. And you can take a photograph of this and submit it. That's fine. Just make sure I can read your handwriting. If you can print it, great. If you can't, screenshot it. Do that, and you can write on, print that, and you can put your calculations in there. Just remember, every time it's the mass retained divided by the total mass times 100 is your percent, and then you take that percent and add it to the previous percent, which in this case is nothing, and put it over here. When you get to the next one, the number 10, you take the mass retained divided by 375, multiply that times 100, and whatever percent that is, put it there and add it to the one before, this cumulative one. And you'll come up with these things and take each 100 minus each cumulative percent, and that gives you your percent finer, or you can call it percent passing. Okay, good enough. Good enough.